Hi there, I'm happy to welcome you to the sixth lecture on radiation protection and the third one in the part 2 of radiation protection. This is on radiotherapy facility design and shielding, and we will look at some practical examples here. The scope of this lecture is that the student should understand the concepts of instantaneous dose rate and time average dose rate in shielding design. Number 2, to learn shielding barrier thickness calculation with some worked out examples. I would like to make it clear here, I have given only one worked out example and I expect the student to refer to NCRP 151 and IAEA Safety Report Series 47 to learn more worked out example, to try more worked out example. I have also discussed some sample bunker designs for C-arm linear accelerator, which I think will be helpful for the student in his career. Let us look at what is instantaneous dose rate and its usefulness. When designing radiation shielding barriers, it is usual to assume that the workload will be distributed evenly throughout the year. Therefore, the barriers are designed to meet a weekly dose limit equal to 1/50th of the annual limit. And therefore, scaling down further would result in greater shielding requirement. In United Kingdom, the shielding designs may take into account the IDR, that is the instantaneous dose rate. The instantaneous dose rate is the dose per hour averaged over 1 minute as measured by the survey meter. What is the advantage of this? In designing with IDR actually helps in comparison with direct measurement after the facility is constructed. What is IDR? IDR is the one that you measure when you do the final survey. That value should be equal to the one that you used for designing if you are using IDR. Then it is easy to compare. This is what with which I designed. Now I am getting the same value. So that way, instantaneous dose rate is quite helpful. The next factor is the time averaged dose rate, TADR. The time averaged dose rate is the barrier attenuated dose rate averaged over a specified time. This specified time could vary if it is for a day, 8 hours, if it is for a week, 40 hours, and if it is for a year, 2000 hours. TADR is proportional to IDR, that is instantaneous dose rate, and includes the workload, use factor, and the dose output rate, which is referred to as DR0 of the treatment unit. The TADR estimated over an 8-hour time of a working day is referred to as R8. The TADR includes the workload for worst case scenario, that is the occupancy factor of 1. The TADR or R8 is the product of IDR and daily beam on time divided by the length of the working day. For example, if there is a 8 hours working day, what is the beam on time for that 8 hours, right? That is what is taken into account in TADR calculation. It will not be 8 hours as it is, but it is the beam on time divided by the length of the working day. Let us look at a little more closely now. TADR is equal to instantaneous dose rate into daily beam on time divided by length of working day, which is usually 8 hours. TADR per day is referred to as R8, which is expressed as IDR into workload for that particular day and use factor divided by 8 into dose rate. R8 is the TADR averaged over an 8-hour day, right, in microsievert per hour. IDR is in microsievert per hour averaged over 1 minute at the point 30 centimeter beyond the barrier. That is where you actually measure where your occupancy is. Not very close to the barrier, it is 30 centimeter beyond the barrier. We discussed this earlier in our lecture 4 also, right? With machine operating at the dose output rate DR0. WD is the daily workload at 1 meter in gray for an 8-hour day. U is the use factor and DR0 is the dose output rate at 1 meter in gray per hour or sievert per hour. TADR 2000 is the time average dose rate estimated over 2000 hours, which is almost a year. That is over a period of an year, assuming 2000 working hours a year. This takes into account the workload, occupancy factor and the use factor. Weekly TADR, it is the TADR averaged over 40 hours per week. That's what I said earlier also. You can have for a week or for a year or for a day. So RW, that is TADR per week, is equal to IDR into the workload per week use factor divided by DR0. Where RW is the TADR for 1 week in sievert per week. IDR is the in sievert per hour when the machine is operating at the dose output rate of DR0. W is the weekly workload. DR0 is the dose output rate at 1 meter in gray per hour. Let us look at some of the instantaneous dose rate limit that is used by US and UK. Right? USA actually doesn't go by the instantaneous dose rate or TADR, but they do use it in their calculation. If you look at NCRP 151, in the examples they have used the TADR, but normally when defining the goal for shielding barrier thickness estimation, they don't use the TADR, right? But United Kingdom, they do use it. Dose limit for occupational exposure is 6 millisievert a year in 1 year. That is in United Kingdom. And IDR is 7.5 microsievert per hour. In USA, it is 0.1 millisievert per week or 5 millisievert per year, right? Whereas the dose design limit for public is 0.3 millisievert in a year. That is IDR is less than 7.5 microsievert per hour. And TADR is less than 0.5 microsievert per hour. And TADR 2000 should be less than 0.15 microsievert per hour. This is for the design limit for the public in United Kingdom. Whereas in the USA, we talk about 0.02 millisievert dose equivalent per week, annual dose equivalent of 1 millisievert. Right? So this is how the United States and the United Kingdom, they have the dose limits. Let us now do a sample exercise. I have taken it from IAEA booklet. This is for a Cobalt 60 facility with an SAD of 80 centimeter. The output at 80 centimeter is 1.25 gray per minute. Assume 40 patients a day with 8 hours work schedule and dose delivered to a patient at the ISO center is 3 gray. The facility is used for 5 days a week. The distance from the ISO center to the wall A is D1 and from wall A to the door is D2. In this exercise, I will do the examples for primary barrier calculation and for secondary barrier calculation, and I leave it to you to do the door calculation. The distance from the primary barrier to the ISO center, that is this distance, is 3 meters, and the ISO center to the secondary barrier is 2.6 meters. The first thing in this will be for us to calculate the workload. We already know that we are treating 40 patients a day with this machine, and each patient gets 3 gray, and that is a 5-day week. Therefore, the workload at ISO center will be 600 gray per week. This is a Cobalt unit, and the ISO center is at 80 centimeter from the source, and the workload is normally denoted at 1 meter distance from the source. So if you apply an inverse square law correction, the workload will be 384 gray per week at 1 meter. If we want to calculate TADR, that is the time average dose rate, we need to know the beam on time per day, and that is given by the total dose per day at ISO center divided by the dose rate at ISO center. The total dose at ISO center we know is 40 patients into 3 gray per patient, which will be 120 gray. And the dose rate at ISO center is 1.25 gray per minute. Therefore, The total beam on time is 96 minutes, which is 1.6 hours per day. Let us first do the calculation of primary barrier thickness. To determine the primary barrier thickness, you need to first determine the barrier transmission factor. The barrier transmission factor equation for primary barrier, if you remember, which we discussed in lecture 4, is this, which is dose equivalent or the design goal into d primary by d0 whole square divided by workload, use factor and occupancy factor. The H, which is the design goal or dose equivalent, in this particular example is taken as 0.12 millisievert per week, which is UK value, not NCRP value. D0 in our case is 0.8 meter, which is a cobalt unit of SAD 80 centimeter. D primary is equal to 3 meters, which is from the isocenter to the point B or A. If you remember, in our discussion earlier, we said the D primary is from isocenter to the barrier plus the barrier thickness, then 0.3 meters beyond the barrier. Let us assume all together now is taken as 3 meters. The workload we calculated to be 384 gray per week at 1 meter. We can take a use factor of 0.25 and occupancy factor of 1. If you substitute these values in this equation for barrier transmission factor, you get a value of 1.81 into 10 power minus 5. Now that we have calculated the barrier transmission factor, we can now calculate the primary barrier thickness. And the equation for that is the number of TVLs required is equal to negative log of barrier transmission factor. Otherwise, you can say log 10 1 by barrier transmission factor. If I substitute a value of 1.81 into 10 power minus 5, which is the barrier transmission factor we determine, the number of TVLs required will be 4.74. The TVL for concrete density of 2350 kilogram per meter cube is 218 millimeter for cobalt energy. This is the thickness of 1 TVL and we need 4.74 TVL. So the thickness of the barrier will be 4.74 times 218, which is 1033 millimeter. We will now determine the instantaneous dose rate and time average dose rate. Instantaneous dose rate is given by the formula output dose rate into barrier transmission factor divided by the square of the distance from the source to the point where you want to know the instantaneous dose rate. If you substitute 0.8 gray per minute to make it into multiply by 60 and to make it into microgray multiply by 10 power 6, you get the output dose rate. And the barrier transmission factor we determined is 1.81 into 10 power minus 5. And the distance from the source to the point where you need to know the IDR is 3 plus 0.8. If you substitute these values in the equation, you get 60 microsievert per hour. To determine the time average dose rate, which is R8, you need to multiply the instantaneous dose rate by the beam on time per day into the use factor and divided by the total hours of work per day. If you substitute 60 here for IDR, which we determined here, and we know that the beam on time per day is 1.6, we calculated it earlier, and the use factor is 0.25 and the total hours per day is 8. You get a value of 3 microsievert per hour. You can also obtain this by dividing the annual dose limit in UK. That is 6 microsievert per year divided by 2000 will give you 3 microsievert per hour. Let us do a barrier thickness calculation based on the IDR, that is the instantaneous dose rate. Let us assume it's a public area and the IDR value is 7.5 microsievert per hour, that is the UK value. The barrier transmission factor for IDR is given by, that is the value of IDRs, that is the design goal, which is 7.5 microsievert per hour, multiplied by the distance square to the primary, divided by the dose output rate, which is 48 into 10 power 6. If you do this calculation, you get 2.26 into 10 power minus 6 as the barrier transmission factor. To determine the number of TVLs, you can take the negative log of the barrier transmission factor, which will come to 5.65 TVLs. We already know that the 10th valley layer for cobalt for energy for concrete is 218 millimeters. So if you multiply 5.65 by 218, you get 1232 millimeter. This is the wall thickness required if you use an IDR value of 7.5 microsievert per hour. And for public area of occupancy of 0.2, the barrier requirement will be 1165 millimeter. I have not done this calculation, but if you look at the IAEA Safety Series 47, you will find you can see this calculation there. In summary, the primary barrier should be 1033 millimeter as we first calculated for controlled area, and 1165 millimeter for public area of less occupancy, that is an occupancy of 0.2. However, I make it say again, as per NCRP, it will be slightly different because they take the 0.3 meters from the barrier, beyond the barrier, okay, which is not done in this case. The secondary barrier thickness determination, as we discussed earlier, will have to be in two steps. That is, you need to determine the barrier thickness for leakage radiation and the barrier thickness for scattered radiation. To determine the barrier thickness for leakage radiation, we assume the leakage radiation to be 0.1% of the primary beam. The distance from the isocenter to just outside the barrier, that is the point here, C, from the isocenter, is assumed to be 2.6 meter in this case. The occupancy factor is 1 and the dose equivalent or the design goal is 6 microsievert per week. The barrier transmission factor equation, if you remember we discussed in lecture 4, is this, and you substitute the values that we discussed now into this equation, you get a barrier transmission factor of 1.06 into 10 power minus 4. As you know, the number of TVLs required is the negative log of barrier transmission factor, and you substitute this, you get 4 TVLs as the requirement for barrier thickness. The concrete wall thickness you can calculate from this will be 4 into 218. 218 is the 10th value layer for cobalt energy. And we need 4 10th value layers, so you multiply this, you get 872 millimeter as the barrier thickness for leakage radiation. The instantaneous dose rate at this point can be determined using this equation, that is the dose output rate into barrier transmission factor divided by 1000 into the distance square, which is 2.6 square. The dose output rate is determined using by multiplying the output per minute into 60, that is the hour, and 10 power 6 is to convert into micrograde. And you get an instantaneous dose rate value of 0.8 microsievert per hour. Let us now calculate the secondary barrier thickness for scattered radiation. Again, let us assume the dose equivalent of 6 microsievert per week, and the d scatter by patient is 0.8 meter, which is our distance from source to the isocenter, and the d sec is the distance from the isocenter to the secondary barrier, which is 2.6 meter. A scatter fraction for 90-degree scatter is taken as 0.0009 per 400 centimeter square of area irradiated. This is from the table. F is the maximum field area incident, which is 400 centimeter square. If you remember, we discussed this in the lecture 4 as 20 by 20 centimeter square. The barrier transmission factor equation, if you remember, is this, but I have not given it here. I'm only substituting the values here. And if you substitute these values in the barrier transmission factor equation, you get a barrier transmission factor of 7.5 into 10 power minus 5. To determine the number of 10th valley layers, the equation again is negative log of barrier transmission factor, which will be 4.12 if you substitute these values in this equation. The 10th valley layer for 90-degree scatter with concrete for cobalt is 151 millimeter. Hence, the thickness required in this case will be 4.12 into 151, which will be 622 millimeter. Apart from learning shielding calculations for radiotherapy bunkers, you also have to have some idea about the planning of a radiotherapy department. To help people understand the planning, IAEA has come out with a master planning document, Radiotherapy Master Planning Considerations. It's a Human Health Report Series number 10. This provides a lot of information, very small booklet, but provides significant information on planning radiotherapy facility, staffing requirement, timeline for project, type of people to be involved in the project, provides sample layout for radiotherapy facility, entire facility including simulator, mold room, everything, where these should be located, etc. And sample layout for external beam radiotherapy bunkers. I will discuss this a little bit. And sample layout for HDR brachytherapy bunkers. We will discuss a little bit on the doorless bunker. I hope you remember we said about it in the lecture 4 that it is possible to have a doorless bunker. If at all possible, how do you do it? Actually, I have taken this layout from the IAEA booklet, which I said that Health Series Report 10, in which they have given two orientations for the radiotherapy bunkers. One is, if you have two bunkers, one is like this, where you can have a mirroring arrangement. One is mirrored onto the other bunker. The other arrangement is parallel arrangement. That is, one bunker is like this with maze here. Other bunker will be identical here with the maze on this side. Anyway, the interesting point here is it is a doorless bunker. How do you achieve a doorless bunker is the question. Now, if you want to have a doorless bunker, the dose here should be very less. How do you reduce the dose here? There are two ways you can achieve this. One is you increase the maze length, then naturally the dose will be less here. And what they have done, you can see, is they have increased the wall thickness here so that the leakage radiation from here that is transmitted through the bunker wall here is less because of the additional thickness. Therefore, they could achieve a doorless bunker here. This arrangement is slightly different to what we saw in the previous slide. If you look at closely, the maze wall is perpendicular to what we saw in the previous slide. This is the arrangement used in most of the bunkers in India and many bunkers in North America. With this arrangement, we were able to get a doorless bunker here. How do you get a doorless bunker? It is by having a small turn and an extension, as you see here. This turn and this extension reduces the scatter dose at this point. So one could achieve a doorless bunker. When I say doorless bunker, I mean no lead-lined door. We will still have a wooden door at least to avoid unauthorized entry. In one of the cancer centers I worked in North America, they had a light sensing door. No physical door, but a light sensing door which will switch off the radiation if somebody walks in. Only concern that you may have in this orientation is there could be radiation from here and there could be radiation from here if both the beams are on, and there could be a slight hot spot here. This is the parallel orientation of the same bunker that we saw in the previous slide. The advantage of this is, as you can see, both the doors entryways are far apart and they don't meet, and the hotspot here is not there in this case. Again, we have doorless bunker because we have this extension and again an additional turn. So the doors here and the doors here will be much less. You can have a doorless bunker in practice. When I say doorless bunker, again, I mean no lead line door. You will still have a wooden door at least to avoid unauthorized entry. This is a brachytherapy facility where the workflow is very convenient. I thought I will discuss this with you. As you can see, this is the HDR brachytherapy room and this is the operation room OR where the application is done. Once the application is done, the patient can be moved to the simulator to do the planning CT for brachytherapy. Then the patient can be in the recovery room or in somewhere in the waiting room here, during which the planning can happen here, and then the patient can be moved to the brachy room for the treatment. So this is a very simple arrangement that could follow the workflow of the patient, right? So the patient movement will follow the workflow. The regulatory board. These are the references I used